Hi, in this video, I'm going to go through the AQA. This is A-level Chemistry paper. This is the 2021 paper. It's paper 1, and it's the second half. I did the first half in an earlier video. Okay. Right, first question is about pH. Okay, pure water dissociates according to this equation, which we're familiar with. Okay. The equilibrium constant Kc is given as that, okay, but we normally use this value, this constant instead, Kw. And it says, why isn't the concentration of water shown in the Kw expression? And that is because the concentration of water is essentially constant. Okay, it's much bigger. The concentration of water is much bigger than the concentration of H plus ions and OH minus ions, and it doesn't really change at all. So that is why it doesn't appear in the Kw expression. Okay, so Kw varies with temperature. Okay, so you can see here, as the temperature increases, Kw actually gets bigger. Okay, now it says explain why Kw increases. All right, so there's 2 marks going for this. Right, so we've got to think about the reaction that's happening here for this. I've got water dissociating H plus ions and OH minus ions, H3O plus really, but you know what I mean. Okay, now Kw is equal to the concentration of H plus times by OH minus concentration. And we can see as the temperature is increasing, Kw is getting bigger. So that means the concentration of H plus and OH minus ions, that's getting bigger. That means as temperature is increasing, the equilibrium is moved to the right. Now, Le Chatelier tells us that the equilibrium will move so as to oppose the change. So if the equilibrium is moving to the right, it will be trying to lower the temperature. So that means it must be endothermic in the forward direction. That is why Kw gets bigger as you increase the temperature, the equilibrium trying to oppose the change. Right. I've just written down the value of Kw at 50 degrees C from the previous table there, because we're going to need that in this calculation. Right, give the expression for pH, of course, is pH is minus log to the base 10 of the hydrogen ion concentration. Calculate the pH of pure water at 50 degrees C. Okay, so we know the pure water, H plus, is equal to the H plus concentration, sorry, is equal to the concentration of OH minus. And we also know that Kw is equal to H plus multiplied by the concentration of OH minus concentration. So because these two are equal to each other, that means that Kw then, substitute the value of OH in terms of H plus, Kw is equal to H plus squared. Right, so now we can find out the hydrogen ion concentration. I'll just go over here. So from this, you know that H plus is equal to the square root of Kw. The value of Kw here is 5.48 times 10 to the minus 14. Square root of that works out to be 2.34 times 10 to the minus 7 moles per decimeter cubed. And now we have to work out the pH of that. So pH is going to be equal to minus log of 2.34 times 10 to the minus 7. Put that into your calculator, you get a value of 6.63. Okay, so now you might think, oh, that's not neutral because it's not 7. Well, that's not true. Explain why water is neutral at 50 degrees C, even though the pH is lower. All you have to say for that is because the hydrogen ion concentration is equal to the OH minus concentration in neutral water. There's the 4 marks for that. Okay, a pH meter is calibrated using calibration graph, which I think this is one of the required practicals during year 13. To create the calibration, the pH meter is used to measure the pH of separate solutions, each with a known pH. Here's the graph, okay. Use figure 3 to give the true value pH when the meter reading is 5.6. Okay, so the meter reading is 5.6, that's about there. Do that line across. Okay, and that means do that down, so that means the pH would be equal to 5. The real pH would be equal to 5.5. Okay. Suggest when you're using a pH probe is wash and with distilled water between each of the calibration measurements, okay, to avoid cross-contaminating the solutions. Something like that. If you look at the mark scheme, we'll give you the mark. Right. The calibrated pH meter is used to monitor the pH during a titration of hydrochloric acid. This is strong acid and sodium hydroxide. So you get the titration curve shown below there. Explain why the volume of sodium hydroxide solution added between each pH measurement is smaller as the end point of the titration is approached. Well, if you look at the shape of this curve here, well, at first, as you're adding the OH minus, the sodium hydroxide, the pH doesn't change very much. But as you get to the end point, the pH changes very rapidly with very small volumes of sodium hydroxide. I think, so you just need to express that. So because the pH is changing very rapidly with very small volumes of NaOH, that happens at the end point. Of course, once you get past the end point and you're up here, then again, there's not much change as you're adding more OH minus. Okay, and now we've got a question about indicators. Okay, the student plans to do the titration again using one of the indicators. And it says, well, basically, why are all of these? State why all 3 of the indicators are suitable. Okay, now you want the indicator to change color on this steep vertical part of the line. That's the steep part of the titration curve, and I think that's actually underlined in the mark scheme. That word steep. You need that. So let's have a look at bromocreosol green. Well, that will be changing around 3.8 to 5.4, so something around there. Well, that's in the steep part. The phenol red, that's 6.8, that'll be changing somewhere there. That's still in the steep part. And finally, the thymolphthalein is that's 9.3 to 10.5, but that is still up here, still in the vertical or the steep part of the titration curve. So all 3 are okay. Okay, now this is a tricky calculation here. It's 5 marks, and we're asked to calculate the pH changes when we add a certain amount of sodium hydroxide to hydrochloric acid. So if we just have a quick look at this curve here, what we're doing is and it's not at the end point, so it's asking us to find out the pH of the solution somewhere along this curve. That's what we're trying to do. Now, if it's before the end point, it's going to be a fairly low pH down there. So that's if the HCl is in excess. If we've added more than enough to OH minus, the OH minus is in excess, then the pH is going to be very alkaline up here. Okay, and the OH minus will be in excess. So if it's this, it's going to be a bit more tricky for us to do it, because we will find out OH minus concentration. And from that, using KW expression, we will find out the H plus concentration, because we know that. So that is a bit more tricky if the OH minus is in excess, and I think it is. If the H plus is in excess, it'd be down there, it'd be more straightforward. We just find out the H plus concentration and then use pH is equal to minus log of the hydrogen ion concentration. Okay, so let's have a look at the question. Right, so what I would do here is, right, you've got sodium hydroxide. So I'd write an ionic equation here. I'd write down OH minus. Right, let's write down H plus. H plus is going to react with OH minus to form H2O. Then I would probably put down here, I put start moles of each one. And here we'll have final moles of each thing in the equation. And finally, we're going to have final concentration. Need to work that out. Okay, so we're going to fill in that little table. Okay, so first of all, let's work out our moles of NaOH. So moles NaOH. That's going to be equal to concentration times volume. The concentration of the NaOH is 0.2 and the volume is 36.25. Okay, so we're going to 0.2 multiplied by 36.25. And of course, we've got to divide that by 1,000, give it in volume in dm cubed. Yeah. Okay, so that works out to be, do it on a calculator, we get 7.25 times 10 to the minus 3 is the answer there. So I'm going to put that in there, 7.25 times 10 to the minus 3. Right, now let's do our moles of HCl now. So that's going to be concentration times volume also. So moles HCl, conc times volume. Concentration of HCl is 0.15 and the volume is 25 centimeters cubed. Not 0.25, sorry. Multiplied by 25 over 1,000. Give the volume in dm cubed, and that gives us a value of 3.75 times 10 to the minus 3. Put that number into our table, 3.75 times 10 to the minus 3. Right, we can see here that the OH minus is in excess. Yeah, so so that means that, because these react together in a 1-to-1 ratio, 1 mole of H plus reacts with 1 mole of H minus, so that's going to go down to essentially 0. Of course, it won't really be 0, it'll be a tiny bit left because you always have a bit of H plus in solution. And the OH minus, well, that is going to go down by that much, isn't it? So it's going to be 7.25 minus this. If you do that, you get a value of 3.5 times 10 to the minus 3. That's how much is left over. And of course, this would just ignoring the water here. Okay, so we've got 3.5 times 10 to the minus 3 moles of OH minus. And the temptation here then is for people then to get confused. I think that's a concentration of OH minus, and it's not. And that will be a pretty common mistake in this. We've got to find out the final concentration. And to do that, we've got to divide. So final concentration is equal to moles over the volume. So what is the new volume? Well, the new volume, look up here, we've added 36.25 to 25. So the new volume, then if you add those two together, is 61.25 centimeters cubed. That one. So let's do our OH minus concentration then. So moles over the vol. The moles is 3.5, we worked out there, times 10 to the minus 3, divided by the volume, 61.25 over 1,000. Volume dm cubed, and that gives us a value of 0.0571 mole per decimeter cubed. We're not there yet. We've worked out the OH minus concentration. From this, we've got to use Kw to work out the H plus concentration. Let's do that. So remind ourselves Kw is equal to H plus times OH minus. So the H plus conc is equal to Kw over the concentration of OH minus. They tell us in this equation here's a bit of a giveaway, the OH minus is in excess because they give us the value of Kw, which is 1 times 10 to the minus 14, divided by this value here. Gives us an H plus concentration of 1.751 times 10 to the minus 13. That's pretty alkaline. So take a negative log of that to give us the pH, negative log minus log of that number there. It gives us 12.756. And they usually want you to give pHs to 2 dP, so that's 7.6. 12.76, sorry. Right. All right, how many marks was that? Was that 7 marks or 5 marks? There's a lot of marks for that question. As I say, the most common place people will go wrong there is here. People forgetting, they work out the moles of OH minus, yeah, but that's not what you want. You want the concentration. You've got to divide by the volume. Okay. Moving on then. Okay, to question 7. It's about thermodynamics. Okay. So we've got this equation of aluminium oxide reacting with carbon, and you should probably know that you can't get aluminium from aluminium oxide using carbon as a reducing agent. That's at GCSE, isn't it? Carbon is not reactive enough, basically. So you know that this reaction won't happen. So we're going to calculate delta G. Assuming delta G is probably going to show us that it's positive and it's not going to happen. Anyway, let's answer the question. 7.1. Explain why the standard entropy value for carbon dioxide is greater than carbon. It's much bigger. It's because carbon dioxide, of course, is a gas, and so it's more highly disordered. Carbon is a solid, more highly ordered. Entropy is much higher. Why is the standard entropy of aluminium, will state the temperature at which the standard entropy of aluminium is 0 joules per Kelvin per mole? Well, that's true of any substance at all. It is 0 kelvins, okay? Any substance will have 0 entropy at absolute 0, okay, by definition. Okay, right, now they are going to ask us what I said they were going to ask. Use the equation in tables and the data. See this equation here, and the data in table sum to calculate the minimum temperature in Kelvin at which this reaction becomes feasible. So how are we going to do that? Well, we're going to use delta G, of course, is equal to delta H minus T delta S, and the minimum temperature is going to say when this is basically equal to 0. Okay, so we're going to say delta G is equal to 0. We will know delta H, we will know delta S, and so we can calculate T, the absolute temperature. That's what we're going to do. But before we do that, we're going to have to use Hess's law cycle to work out delta H for this reaction. So that's what I've started drawing down here. Okay, so we want to find out, they've given us delta HF data here. Now, whenever you do that, you want to have the third thing in the Hess's law cycle, you want the elements in their standard states at the bottom there. That's what I've got there. Okay, and the arrows are going to go up because you, of course, you're forming aluminium oxide, in this case, from its elements in the standard state. And on the other side, you are forming 3 moles of carbon dioxide from their elements in their standard state. That's what's the energy change for this green arrow? Well, 3 moles of carbon, nothing happened to that, so we ignore that. But we're forming 2 moles of aluminium oxide, so that is going to be 2 times minus 669 there, which if we work that out, that is equal to minus 3338. On this red arrow on the other side, we're forming 3 moles of carbon dioxide, so that's going to be 3 times carbon dioxide minus 394. Work that out, that's equal to minus 1182 kilojoules. Okay, so now we want to work out this value of delta H. Okay, so what we're going to say, delta H, scroll up a little bit. Delta H, the blue delta H. Right, we are going against this green arrow here, aren't we? So we're going to change the sign there. So that's going to become a positive. So that's going to become 338. And we are going up the red arrow with the sign. So we keep that. Don't change it with the arrow. So we don't change the sign. 1182. And that works out to give us a pretty endothermic reaction value of plus 2156 kilojoules. Okay, now we need to work out, so we're going to put that into our delta G expression, but now we need to work out delta S. Okay, so right, let's work out delta S. So let's look at that. Let's look at the equation there. I'll just rub this out. Right, to work out delta S, we need to know the entropy of the products, which are doing green, and we subtract the entropy of the reactant, which is in red. So let's say delta S is equal to, well, the products, got 4 aluminiums, 4 times 28. And we've got 3 carbon dioxides, which is 214. And then that is going to give us, sorry, no, we've got to put in the minus yet, so we're going to have to, sorry. And so we need the entropy of the reactant, so that's 2 aluminium, so that's 2 times minus 1669 times, not minus, sorry, times, sorry, 2 times minus 1669, square bracket there, and plus the entropy of the carbons, which is very low, 3 times 6, and do that in my head, is 18. Right, so we do all that on our calculator. The green value comes to 754. Subtract the red stuff. That comes to 120. Sorry, I'll put a completely wrong value in there. Should be 51, of course. I put the delta HF value in there. So that's going to be minus 120. And that gives us a value of 634. And we've got to be careful here. The units is joules per mole per Kelvin, not kilojoules. So we're going to have to convert that into kilojoules, or we can convert the delta H value into joules. But I prefer to do that. So that's equal to 0.634 kilojoules per mole per Kelvin. Okay, so we've got our two values of delta H and delta S. Now let's write down what we've got to do with them. Right, so let's do that here. So delta G is equal to delta H minus T delta S. Now the reaction becomes feasible when delta G stops being positive and actually becomes 0. So we want that when delta G is equal to 0, that's the minimum temperature. So when we do that, we're going to get 0 is equal to delta H minus T delta S. So T delta S is equal to delta H. We need to find out T, the absolute temperature. So T is going to be equal to delta H over delta S. Delta H we worked out to be 2,156 plus kilojoules per mole. Delta S we worked out to be 0.634 kilojoules per mole per Kelvin. So that gives us a value of 3,400, and of course the units are going to be kelvins. So that reaction shouldn't be feasible until you get to 3,400 Kelvin, which is of course very high temperature, which that sounds common sense. We've got the right answer there because we know this reaction shouldn't really happen at normal temperatures, and it doesn't appear to be feasible until the temperature becomes very high. Okay, so 7 marks there. It's a fairly standard question, but I suppose there's a lot of places where you can make little mistakes there. Okay, on to electrode potentials. Okay, state the meaning of the term electrochemical series. And I think all they want, it's only 1 mark. They just want you to say when you put electrode potential values in order, either from positive to negative or from negative to positive. You look in the mark scheme, that's all they want you to say for that. Okay, so we've got some electrode potentials there, all to do with transition metal complexes mostly. Okay, right. State 2 conditions for the following half cell to have an E of 0. Well, this is a special one. This is the standard hydrogen electrode reaction, isn't it? So for it to have a value of 0, you've got a standard condition. So you want 298 Kelvin. Not 29.8, 298. My pen made a mistake there. 298 Kelvin. Also the concentration of the hydrogen ions should be 1 mole per decimeter cubed. And there's another thing you can say, it only wants 2, but there's 3 possible answers there. Because you've got a gas, okay, the pressure of the gas should be, now I would have put 1 atmosphere. If you look in the mark scheme, they don't like that anymore. You've got to say, what is standard pressure? 100 kilopascals. Okay, so any 2 of those 3 you can say. Okay, identify the weakest reducing agent, table 8. Okay, so what are the reducing agents? The reducing agents are these things on this side, because when they go backwards, they give away electrons, don't they? Okay, so these are the reducing agents, give away electrons. Who's the best at giving away electrons there? Well, it's going to be the most negative, because if it's more negative, it's going to push electrons away. If it's more positive like this one, it's going to be better at pulling electrons towards itself. So the strongest reducing agent in that table is iron metal, Fe. Again, it's a very standard question for this topic. Okay, now use half equations from table 8 to deduce an equation of the reaction for the reduction of the dioxide of vanadium ion to form this ion in aqueous solution by ion. Okay, now that is a bit mean, that question. And right, by the way, they only want 2 marks there because you've got a couple of things going on here. Okay, so what do we need to look at? We need to look at iron reacting with dioxide of vanadium. So obviously we want this equation here, this half equation, and we want this one here. Okay, what's going to happen there is that, okay, the vanadium one is the most positive, so that's going to go forward and take in the electrons, that's going to go forward, and the iron one is going to go backwards and give out the electrons and form the Fe2 plus ion. But that is not where it will stop then. If you just combine those two half equations, to give you a full equation, you multiply the vanadium one by 2 and so on, you'd only get one of the two available marks, because you've also got to realize, and they don't make this clear in the question, I think it's a bit mean, that this one can then react with this half equation here. Look, it can oxidize Fe2 plus further to Fe3 plus. So we need to bear in mind we have got the following reactions here. We've got the vanadium one, okay, we've got that, and that's 1 electron, and that's going to go forwards. Now it's going to go, first of all, it's going to turn the ion to Fe2 plus, and that's 2 electrons in this equation here. And then it's going to oxidize it further to Fe3 plus, which is 1 more electron. Okay, so that means this is 3 electrons altogether for this set of reactions. So this one is only 1 electron, so we're going to have to multiply this one by 3 and then add them together. So let's do that. Okay, so we're going to have, let's do, I'll go down here and do it. Let's do the trickiest one first. Let's do the iron. Okay, so the iron is going to go from Fe solid, and then you're going to have 6 waters, and then that's going to lose 3 electrons to form Fe. Three plus, put 3 electrons there, and the dioxide of vanadium one is more straightforward. We've got VO2, and we need 2 protons, 1 electron to give us that, and a water. So we're going to have to times this one by 3 and add them together. So let's do that. And as the final thing, we're going to get right. So 3 VO2 plus plus 6 protons plus 1 iron and 6 waters to give us the 3 plus complex. And we're going to get 3 of those. And we're going to get 3 waters. But we can do a bit of cancelling of waters out here, because we've got 6 waters there and we've got 3 waters there. So that means we get rid of 3 from both sides of the equation. They go, and that becomes 6 minus 3 gives us 3. So that's our final question there, final equation there, sorry. Okay, so right, I've just copied the table again for this part of the question. Okay, use the data from table to explain why the cobalt 3 plus ion will undergo a redox reaction with the Fe2 plus ion. Well, let's look at the 2 equations that we need. The aqua complex cobalt there, and the we need to find one with the 2 plus ion, the Fe2 plus ion. So that one there. Look at those 2 half equations. Which one is the most positive? It's the cobalt one. That's going to be best at taking in electrons. That is going to go forwards. The iron one is the most negative. That's going to be best at pushing away electrons. That's going to go backwards. Okay, now for the explanation, all you need to say is that this half equation, that one there, is more positive than that one. That's all you need to say. You don't have to mention anything else. Now the equation, right, we've got to combine those two half equations. We have got, each one is one electron, so we don't need to do any multiplying, we just need to write it down. So we're going to have there, we're going to have cobalt, H2O 6, 2 plus, 3 plus, sorry. It's going to react with the Fe2 plus. So the cobalt's going to become 2 plus. And the iron is going to be oxidized to the 3 plus oxidation state. Okay, so that is that there, okay. Right, suggest why the two cobalt-3 complex ions have different electrode potentials. Okay, so we look at the, let's look at the data here. Let's just rub some of that out. So what we're looking at, we need to look at, looking at that one and that one. Or what's the only difference between them is they've got different ligands, and that's all you need to say. Is you need, for that question is you need to say they are have got different ligands. You don't have to explain why having different ligands would give you a different electrode potential. It's a bit more difficult. You don't need to say that. It's just a 1 mark question. Just say different ligands. And incidentally, why would having different ligands make it easier for the change the electrode potential value? Well, it would make it easier or harder for the central metal ion to lose or gain electrons, because of course you've got electrons. The central metal ion is interacting with the electrons in the ligands, and those, well, if the ligand is different, the electron density of the lone pair in the ligand is different also. Okay, so this is about lithium cells. Okay, the first one is not the lithium ion cell. This, okay, this is something different. So we've got electrode potential data there for lithium reacting with water. Okay, so explain why an aqueous electrolyte is not used for a lithium cell. Right, if we have a look at this, it's because lithium will react with water. As we know from GCSE, alkaline metals will react very rapidly with water. Lithium will. And how can we show that using this data? We need 2 marks. You can't just say lithium reacts with water. To say why it reacts with water, we'll look at that half equation and that half equation. Right, you have got, this one is the most positive, so that will go forwards, and this is by far away the most negative, that will go backwards. So you need to say it's because that half equation is more positive than that half equation. That is your explanation. Okay, that's why lithium will react with water. Okay. Right, in the 1970s, lithium iodine cells became power source for heart pacemakers. Lithium iodide is the final product of the cell reaction. Use the data in table 9 to calculate the EMF of the lithium iodine cell. Okay, so we need to look at the 2 half equations which we're interested in, which are these 2. Of course, we're going to get that one going backwards because it's most negative, and this one going forwards because it's the most positive. We're going to have E cell is equal to E right minus E left. Now the convention is always to put the most positive on the right hand side. The most positive one we have got here is the lithium, so that's 0.54. Sorry, it's the iodine, sorry. 0.54. Minus the E left, so that's minus, and the minus 304. Okay, so do that, and what you get plus plus 3.58 volts. Okay, so that is the answer to that one. Right, now it's going to ask us why And so you get 3.58. The next question is, an EMF value for a commercial lithium ion says it was quite a bit lower than that. It's 2.8 volts. Why is it different, the value calculated in 9.2? Well, for 9.2, we used standard values, didn't we? Yeah. Standard conditions, okay. And obviously, there aren't standard conditions in the battery. The ion concentrations are different at something, so the EMF is different. Okay, in some lithium cells, lithium perchlorate is usually electrolyte. Deduce the oxidation state. Okay, so what I would do there is we know that lithium is a group 1 element, so it's always an Li plus ion compounds in it. So that means this perchlorate ion has got a -1 charge. Okay, so, and then I would use this little sum of the oxidation numbers is equal to the charge on the species. Because the charge on this species is 1 - 1 up there, yeah. And we're ignoring the lithium, but we're just talking about that species. So we've got chlorine is unknown. Oxygen, of course, is always -2, and there's 4 of them, so that's going to be -8. So just a bit of algebra there. Cl is equal to +7. The oxidation state of chlorine is +7. Okay, now this is a bit of a mean question because 9.5 and 9.6, the last two questions on the paper, this is a bit of you need a bit of recall here. You need to remember it's actually about cobalt oxide electrode, and you need to know that they don't give you the equation there. The equation for that is you get COO2, and that can be reduced 1 electron to COO2 minus. Okay, so that's how you can write it, and that is what's going to happen as well. This is the most positive, this one, okay? In the lithium ion battery, it's most positive, so that one is going to take in the electrons. That's what's going to happen when you discharge the battery. Sometimes people put in lithium ion there, okay, so you have Li plus there, and they put Li plus in there, because of course the lithium ion actually goes inside the cobalt oxide electrode. So you can have it with those red bits in or without those red bits in. And then you need to, the last question, 9.6, give an equation for the reaction because the negative lithium electrode, well, that's more straightforward. The lithium just loses an electron, very negative, to form an Li plus ion. There's that there. Okay, so that would be the reaction happening at the negative electrode. That is the end of the paper.